Welcome to class today, folks. It's Monday, April 26, 2021. Believe it or not, we only have 4 weeks of class left. We have this week, which is obviously the last week in April, and then we've got really 3 weeks of class. I'm not even sure if it'll be that many. I think maybe you all will just be here for 2, and then we'll have a week of virtual learning. So this week will be the last week of Unit 9. We've got 1 more unit after this. And then we're going to have 2 weeks to review for the EOC, which, like I said, is, I think, going to be really helpful for you all. But I just want you all to come into this week feeling positive, feeling productive, feeling like you can get your whatever tasks and goals you've set for yourselves done. It's always a great idea to come into the week and try to think about, what is your week going to look like? What help might you need to enlist? Whose help might you need to enlist? What does time management look like this week? So I'm glad we got that message from SGA, but I want you all to always remain positive and just feel like each week is an opportunity to do something new, to try something differently, and to apply yourself in a different way. I keep forgetting to change the date on my whiteboard. But today we are going to talk about population growth. This is probably, pretty simple stuff. We've got some definitions that we will introduce to you all, but I think for the most part, this will be pretty intuitive information. The objective is to explain why ecosystems can be relatively stable, even though populations living within the ecosystem may fluctuate. And then the essential question, I keep forgetting to change the essential question. All right, let me do that. All right, that's better. So we've got 2 essential questions that I just came up with off the top of my head. Number 1, how do populations grow or stabilize based on their environments? And the second one is, how does growth affect the environment? So we've kind of got 2 things going on here. We've got the environment having an impact on the growth of the population, but we also have the growth of the population having an impact on the environment. So I see Pedro and Breon have their notebooks out. I know a couple of you take notes virtually, but let's make sure that we're ready to take notes during today's lesson, especially my folks at home. I cannot see you, but I do trust that you're doing everything you need to do to stay up to date with your note taking. And guys, as we get, we're less than a month out from the EOC exam. I think it was exactly a month from yesterday. It's important to remember that simply writing down notes one time isn't going to do all that much. In fact, it might even be more beneficial if all you're planning on doing is writing, to just make sure that you're listening really intently. But if you are writing, then you should be going back to read what you've written. That's the only reason that you write things down, to record it for future use. Okay, so I encourage you all to do that as often as possible. Just dedicate 10 to 15 minutes every day, even if it's downtime during class. If you're like, okay, I finished writing on this slide, but Mr. Rudd hasn't changed the slide yet, let me just flip back and check out some of my notes from past days. It's a great idea. Dedicate 10 to 15 minutes a day, 2 minutes here, 3 minutes there, while I'm on the bus, while I'm whatever. So just looking at old notes, that'll go a long way. Trust me, that's what the top students do to separate themselves. All right, so I've got a couple questions for you. So what we're seeing here is an interesting map, and it's an animation that's showing how population has grown over the last 200 plus years, and then also how it's expected to grow over the next 80 years or so until 2100. what are you all noticing in this map? Where is the population expected to grow the fastest? If you're looking in this animation, where is it expected to grow the fastest? And just to make it a little more clear, maybe that's what we're struggling with. The populations that are growing are kind of swelling up. They look bloated. Okay, so the very first right here, that represents the normal map, right, without any distortions. But the distortions, as the countries are either shrinking or bloating, are representing the populations that are growing or that are not growing, maybe even shrinking. Hello, Sade. Thank you for coming today. So where do we see population growth, or where are we expected to see population growth happening the fastest? Any thoughts, or are we confused? Somebody say something. Hello? Okay, so thank you, Ayana. So we can see that in the past 200 years, 1800, 1900, and even up till now in the 2000s, the green countries have experienced a lot of growth. That's why they're so bloated. That's why they look so swollen. They're taking up a huge portion of the map. What are those green countries? What region of the world is that? That's not Europe. A little bit further east of Europe. Somebody said something. Asia, thank you. So the green countries are the Asian countries. So we saw in the 19th and 20th centuries huge growth rates in Asia. China's population and India's population expanded rapidly. They are now the two largest countries in the world. India is the largest democracy in the world. China is the largest, most populated country in the world. Both of them have over 1 billion people, which is at least 3 times larger than the United States. Hard to imagine that many people live in one country. But let's look at that very last circle, the 2100. Where do we see growth happening there? In the very last portion of this animation, which country or which color is the biggest then? Thank you, Abraham. Yes, this is Africa. So when the circle gets to 2100 right now, we see the orange countries become the largest, and that is the continent of Africa. So we are expected to see the most growth in the next 80 years take place in Africa. Does anybody think they might know why that is? Why are we expected to see so much growth take place in Africa? You've got a thought, Ayana? Okay, that's very true. So more land is being cleared for living, meaning that it's being urbanized. So a lot of land that was maybe previously farmland or meant for cattle grazing is now being urbanized. It's becoming a city-like environment or maybe a suburban environment. And that definitely means that there's more space and people don't have to spend all their time on farms. Any other reasons we can think why the population might be growing in Africa so quickly? What'd you say? Okay, good. There are a lot of job opportunities, and more importantly, well, not more importantly, but aside next to that, are investment opportunities. So we know that there are a lot of countries and companies that are investing a lot of money into African countries. That's a good and bad thing, for social reasons, but we won't get into that for now. But that's a great point. Yeah, a lot of people, because there's more money available, more people can work and more people can support families. Any other reasons we might think of why a population might be growing? Human population. Why do human populations grow? I see at least three people on their phones who are not even trying to answer the question right now. Why do populations grow? Human populations. What what's like the most basic thing that has to happen? Yeah, more people are having babies. Thank you. So especially this is kind of an unfortunate thing, but in Africa, uh, there's not really a sex ed program, and there aren't that a lot of people don't have access to contraceptives, and unfortunately, there are higher incidences of rape taking place in some African countries, and so because of that, there are a lot of babies being born. This also leads to other um, phenomena like the spread of STDs, which is, HIV is still pretty rampant in Africa. So because there aren't contraceptives, meaning, condoms, birth control pills, um, IUDs, these things are not available to some African women primarily. And so they don't have as much control over their family planning, meaning they're having a lot of children. And that's also contributing to the population growth. Okay, so what are the dangers of such exponential population growth? What could go wrong when your population is growing so quickly? I'd love to hear from somebody I haven't heard from yet today. Rian, Rudy, Fraylin, Pedro. What are the dangers of a population that's growing so quickly? What could go wrong? What kind of supplies or resources are we talking about? Exactly, exactly. Chandler mentions food shortages. That's going to be a huge problem. It already is a huge problem. You could literally run out of space where people don't have enough. They're living on top of one another. Oftentimes, that means that they're living near waste, so that's very unhealthy. They might be living in polluted areas. Again, very unhealthy. You mentioned water as well, Sade. That's also a big problem and will continue to be a problem. We have obviously a lot of water on the planet, but most of it is salt water. It's not drinkable. So there's a limited supply of fresh water. Good. Thank you, Brianna. Less natural resources. Anything else that could potentially go wrong with such a quickly and growing population? Wonderful. Thank you, Chandler. Yeah. When you've got so many people, there's only a certain amount of medical care that is available. We can even think about the COVID-19 vaccine right now. It's in limited supply. And especially in countries that are, number one, poor, and number two, have a lot of people, they don't have nearly as many opportunities for people to get vaccinated. And that's just one virus. So, of course, the same thing is true for a lot of different types of diseases where the opportunities to get medical care just aren't there. Anything else we want to mention here? I think we've done a good job. We've covered a lot. You got something, Ayana? Would you say? Overpopulation in general, yeah. Again, when people are living on top of one another, it tends to lead to disease, the spread of disease. It tends to lead to a lot of people living in poverty, and people who might otherwise be able to support themselves living on a farm might be dying of things like famine. So again, uh, if the population is growing rapidly, oftentimes the social infrastructure is not there to support it, meaning that the economy has not yet caught up. The hospitals have not yet caught up. The schools have not yet caught up. And so you find yourself in this middle ground where the population is growing, but the environment can't support the population. Excellent job. Thank you for that conversation. Make sure I change my attendance. Okay. So here's a definition for you all that you should definitely write down. But it seems like you all, again, this was pretty intuitive. We had great responses from Sade, Breon, Chandler, Ayana. They were basically getting at these limiting factors. A limiting factor is a biotic or abiotic variable. So it could be living or non-living that constrains a population size and prevents it from growing exponentially. So what you're seeing in these images, I'm trying to do stuff for the animal kingdom on top, and then pictures that represent the human populations on the bottom. So food is a very common limiting factor. We see in that image on the top left, beetles that are eating some type of plant, but it's clear that the plant is basically depleted. There's not much left to be eaten. Same thing with human beings. With us, the problems can be a bit more pronounced because our problem is not just how much food can we produce, but how long can it last? You know, if we're trying to produce food in Chile, for example, and it needs to be shipped all the way here to Charlotte, North Carolina, we've got to do stuff to it so that it doesn't spoil before it gets here, which requires the use of chemicals. It requires a lot of money to be spent on refrigerated trucks and planes and ships, cargo containers. So we have to put a lot of money just in being able to transport food from one place to another. Land is a limiting factor. Of course, land is abiotic, but we can run out of land. That can be a problem. And again, when people are living in such close quarters, living in close proximity to one another, the spread of disease is more likely. Poverty is more likely. Lack of job opportunities is more likely. Water, another abiotic variable that can also be a limiting factor. Currently, there is a war being fought in a country called Yemen, basically over the inaccess to water and food. So we're already seeing lack of access to water be a cause for actual war, for bloodshed. And it's going to continue to happen, unfortunately. Same definition there, so there's nothing new to write. But temperature is an abiotic factor that can limit a species' growth rate. So, of course, we know that human beings are not capable, and really no life forms are capable of living in Antarctica, at least not permanently. And at the same time, only certain life forms can live at higher temperatures. So the Great Barrier Reef, which is off the coast of the eastern coast of Australia, it used to be one of the most biodiverse places on the planet Earth. But because of the rising sea temperatures, many of the species are dying, including species of coral that will never come back. They're going extinct. It leads to this process of bleaching. So the coral that used to be these really vibrant colors, these different hues of red and orange and green, are now turning white, which is the symbol that they are their enzymes are being denatured and they're dying off because the water temperature is too hot. Mates, you know, the ability to find well, not a spouse, but someone to have offspring with, can also be considered a limiting factor, a biotic limiting factor. Some species are able to reproduce quickly. There are some species that reproduce multiple times in a single year. And then there are other species that might only reproduce once over the course of several years. There are some species that stay with the same mate. Human beings typically stay with the same mate. But there are other species that basically just find, you know, the first available mate. All right, but these things contribute to how often a mate can be found and how often offspring are had. And then altitude might be a limiting factor, and another abiotic factor. So in general, we think of these four factors as influencing the actual rate of growth. Number one, the number of births that are taking place in the population. And Sade, that's kind of what you were mentioning too. Of course, you got to have babies for the population to grow. Number two, the number of deaths is going to influence the growth rate. Mm-hmm. Even if people are having a lot of babies, but some of those babies are dying before they reach the age at which they can have their own children, then the population is not going to grow, right? And we know that this has happened in the past. In the 18th century, we didn't have the medical capabilities that we do now. And people would have a lot of kids because they might be living on a farm and they might need to support all of their, they might need to have their children work on the farm with them. So they might have 6, 7, 8 kids. But it was almost guaranteed that at least one of those children was not going to survive to adulthood because of disease, because of accidents while they were working. And so, of course, that limits how fast the population can grow. Right, Brian? The availability of resources can also impact or influence the rate of growth. And that's something that we heard from pretty eloquently from Chandler and Sade and Ayana. And then competition as well. And we've talked a little bit about competition. We'll say a little bit more about it on Wednesday. But the competition for resources, for mates, for land, we know that a lot of species are very territorial for these very reasons. Okay. Okay, so in general, there are two types of limiting factors. There are density independent factors, and then there are density dependent factors, which we'll define on the next slide. Brian, can you read the definition for a density independent factor for us? Can you see it? Good, thank you. So a density independent factor does not rely on how many individuals there are in a given area. So there could be one individual or there could be 1,000. These types of limiting factors are going to limit the growth rate of the population regardless of how many individuals there are. So temperature, again, if we drop off one human being in Antarctica, probably won't grow. The population probably will not grow. But if we drop off 100 human beings in Antarctica, again, population is probably not going to grow. It has nothing to do with how many individuals there are. It has everything to do with how harsh the environment is. The temperature just doesn't allow for much life. Natural disasters are also density independent factors. So if we've got a mudslide and it starts to roll down a hill and there's only one tree on the hill, the mudslide is probably going to kill that tree because it's going to wipe up its roots. It's probably going to uproot the tree and push it out of the ground. And if there are 1,000 trees in that same plot of land, the mudslide could still wipe out every single tree. Same thing with the forest fire, same thing with a hurricane or an earthquake. These natural disasters don't really depend on how many individuals there are in a given space. They really have an impact regardless of how many there are. And we can even think about oxygen levels underwater. If oxygen levels, drop, then it's not going to be able to, the environment won't support life. It doesn't matter how much life is there in the beginning, it just won't support life. So those are great examples to have, guys. One thing to keep in mind is that when you're taking exams, it's nice to just be able to have some examples. That makes things a bit easier to remember as you're moving through an exam. So once you've written down the definition, it's not a bad idea to consider writing down these 3 examples. Should be pretty quick. And then there are density dependent factors. These are factors that influence a population's birth or death rates. And their effect is based on the density of the population. So how many individuals are living in that space, that matters. Disease, bacterial disease, and even viral disease is a great way to think about these density dependent factors. Because over the last year, we've talked a lot about social distancing, and we've talked about quarantining. The reason we do those things is so that the virus could not spread. The virus spreads when human beings are in close contact with one another, when they are in a high density space where there might be 30 people in a room. Go ahead. If there are only 2 people in a room, even if one of them does have the virus, it can only spread to one person. So the overall impact on the population is not going to be very large. Competition, of course, individuals don't need to compete as much if there aren't that many of them present, if they might all be from the same pack or from the same school of fish. They don't need to compete. But if there are, a lot of individuals living in the same space, then the competition for land, the competition for food, the competition for mates becomes much more serious. One, two, three, four, five, six, seven, eight, nine. Okay. Freon, you got to stay with us. Stay with us. Sleepy day, long night of playing Warzone or something. 2K. I don't know what it was. What box is this? Second box? What'd you say? This is that one of those points in the class where we've got some downtime. You might scroll up in your notes to check out something we've written in the past or flip back a couple pages. Just use your time wisely, guys. That way you don't have to worry about taking it out when you get home. You can just do it now. Do some review. Try to make some connections between what we're talking about today and something that we talked about in the past. Density, yes. All right, so this is kind of just of interest. Maybe you guys will find this intriguing, but currently the human population is probably even bigger than that now. This is from several months ago. Is at 7.8 billion people. 7.8 billion. Is that a big number? Is that shocking to hear? 7.8 billion people. How many of you knew that it was that large? Raise your hand. Only one person. Okay. Yeah, it's shocking because when I was in high school, when I was your age, there were only about 6 billion. So, in only the last 10 years or so, the population has increased by almost 2 billion people. So that, again, demonstrates just how quickly the population is growing. It's kind of hard to see this map, this graph. But what it shows is that in 1820, the population was only about 1.2 billion people. I guess 1 billion people. Right. So it's been 200 years, and we've seen the population of human beings on Earth increase by almost 7 billion. Okay, so that's humongous. That's such fast growth. And you guys tell me, why has the population grown so much over the last 200 years? What do we think? A lot of reproduction has taken place. Yes. Yeah, a lot of babies have been had. But what else? What's been like the biggest historical development in the last 200 years? Alex. There have been a lot of medical developments and a lot of medical innovations for sure. And what kind of spawned all of these innovations? There's one event. Of course, the event took place over years, but we have a name for it. A birthday. It's a type of revolution. Thank you. The Industrial Revolution. All right. So the Industrial Revolution took place in the late 1800s. And that's when, if you look at the graph, you can see that's when the population really took off and started to grow rapidly. That's because the Industrial Revolution made a lot of people rich. It also put a lot of money into science and into research and development. And so we developed new medical technologies, as Alex talked about, which meant that more babies could be born healthier. Mothers were not dying in childbirth as much. People could survive specific diseases that they may have died from, only years prior. We're, of course, still seeing advances in technology, right? People used to get cancer diagnoses 100 years ago, and it would basically be a death sentence. Now, many types of cancer can be and will be survived. We know there are specific genetic disorders that used to be deadly for people, but now they can live well into their 30s, 40s, 50s, and they can have children of their own. So because of these advances, as Alex mentions, we're not seeing as many people die. And we also saw a lot of people being born as well. So let's see. All right, so this is fascinating stuff. Just today, 150,000 people have been born. I mean, is that not mind blowing to you all? That's hard to even conceive of. 150,000 people. Um, to put that into perspective, that probably means by the end of the day, there will be basically the entire city of Charlotte will have been kind of reborn. Of course, it's not all happening in one place; it's happening across the entire planet. But that tells you how quickly things are happening. On the other side of that, 63,000 people have died today. And again, this is happening all over the planet. Would you say? 63,000 people have died today already. Yes. But of course, in other places around the world, the day is ending, you know. Um, but yes. So that means that overall, the population just today has grown by 87,000 people. And it's only 9:24 a.m. on the East Coast of the United States. All right. So the day is not over yet. And we've already seen nearly 100,000 people be added to the world's population. This year, of course, it's only April 26th. This year, we're not even 5 months into it. The population has grown by 25 million people. So, of course, we're seeing, the Earth's population grow rapidly. We call this type of growth exponential growth. So we see the current population is at 7.86 billion. By the time some of you are done with high school, it'll be above 8 billion. Yes. Now, of course, this isn't like reading all the birth certificates, but nothing like that. This is based on a statistical model. Yeah, so you can see, I mean, every second it looks like 3 to 4 people are born and 2 to 3 people are dying. Amazing stuff. This was something I meant to show you all earlier. But we mentioned that food is a limited resource, and it truly is. This is the hunger map from 2018. It's showing where a lot of the biggest problems with famine are today. So this is showing the percentage of undernourishment for the total population. The darker red countries have 35% of their population and over are undernourished. Today, about 1 in 9 people across the planet do not get enough to eat. And it's not just happening in Africa. We see Southeast Asia, we see some South American countries, Central American countries also having these issues as well. 1 in 9 people do not get enough to eat. All right. All right, so you just heard me use this term in reference to human populations. I said exponential growth. This is growth that is happening rapidly due to typically an unlimited availability of resources. I use that term cautiously because we know that in theory, there's never going to be an unlimited availability of resources. When we graph populations that are growing exponentially, it literally looks like the letter J, a capital J. So we sometimes will refer to this type of growth as a J curve. Bless you. So with exponential growth, one becomes two, and instead of two becoming three, two becomes four. And then again, instead of four becoming five or six, four becomes eight. And then eight doesn't become 10 or 12, it becomes 16. So we see the population is growing rapidly. The numbers are increasing very, very quickly. But like I said, there's no real such thing as unlimited resources. We don't really see that in nature, right, Sade? You always, as you mentioned earlier, will have limited resources. That's the exact phrasing you use. And we can actually calculate how much a population can grow based on that number of limited resources. Populations can only get so big because eventually they will run out of space, food, mates, they will run out of water, all of those limiting factors that we previously talked about. So that number is called the carrying capacity. Each environment has its own unique carrying capacity. It can support a specific number of organisms within the environment. Environments that are nutrient rich, that have a good source of fresh water, that don't have any extreme weather events, these typically have a higher carrying capacity. So you see a lot more life there. You see more biodiversity. You see larger populations. We can think about the African safari as being one of those places. We can think about the Amazonian rainforest. We can think about the Great Barrier Reef. These are all places that have great resources, and so they can support a lot of life. Other places are more barren and they might be more harsh, so they just can't support that much life. They have a lower carrying capacity. We can think about desert environments. You might find some life there. You might have the occasional cactus. You might have the occasional insect, maybe a snake or some type of reptile. But for the most part, it's not teeming with life all over the place. So it's got a lower carrying capacity. So if we're looking at this graph, Gloria, I haven't heard from you. I see you've been taking notes though. What does it look like the carrying capacity is for this environment? How many organisms? Would you say? What's the carrying capacity? So how many organisms can be supported by this ecosystem? So where does the graph kind of level off? How many? 1.5, and in this case, it's 1.5 million. Correct. Good job. Thank you. So once we see the population gets to 1.5 million, it goes up a little bit beyond that temporarily. We can see it goes up beyond 1.5, but then it comes back down because unfortunately the environment is not going to support all of the organisms. So some of them die, and then it goes back up a little bit above 1.5, but then it falls back down again, and then it goes up and then it falls down. So this type of kind of cyclical movement, increase and then decrease, increase, decrease. We refer to that as dynamic equilibrium. Dynamic equilibrium, because on average, we're seeing the population is about 1.5 million. But there are times when it's higher than that, and there are times when it's lower than that. So it's at equilibrium, meaning that it's not change. It's pretty stable, but it's dynamic equilibrium, meaning that it's changing a little bit. It's fluctuating. All right. So there's exponential growth, and then there's also logistic growth, and this is why we just defined the term carrying capacity. Yeah, I did. So which would you rather your bank account be? Exponential growth or logistic growth? Ex- Exponential or logistic? Oh, you all must not like money around here. So logistic growth is clear. It starts to level off. It stops growing at a certain point. So you wouldn't want your bank account to do that. You always want your bank account to keep growing. So exponential growth is obviously preferred. Logistic growth is growth in which the growth rate levels off as the population reaches its carrying capacity. And of course, this is due to limited resources. So again, this actually looks like a capital S a little bit. So sometimes we refer to this as an S curve. Okay. All right. So we've got 10 minutes, 12 minutes actually. I think you could actually get the assignment for today done. It's actually called, I'm going to change the name to Investigation of Population Growth. It's Unit 9, Day 3. If you don't want to start that, then you can just knock out the exit ticket, which is, of course, Unit 9, Day 3 exit ticket. But we should be doing something productive for the last 12 minutes of class. Which exam is it? Uh, to report to, so at 10 o'clock, that's going to be during hawk time. You'll go to room 111. You're welcome.
Can I go to the bathroom?
Yes.
Investigation of population.
Correct.
Attention to the area. Teachers, please check your email from Ms. Dockett. Please check your email from Ms. Dockett regarding the panorama survey. Please make sure all of your students take the panorama survey today. We can try to make that part of the next activity of some type. Also, shout out to our Cambridge team in the media center. Ms. Forbes, Ms. Burke, all the students taking the Cambridge exam, also Ms. Stephanie, who's on campus. We appreciate your hard work. We're done the great things about you. Once again, please make sure all students take the panorama survey by the end of the day. Please utilize talk time to maximize this opportunity.
See you all. Have a great day. Bye, Mr. Rudd. You too. Yeah, you always say bye. We'll give you that. Thank you, Sade. No, I do not. You're gonna have to listen to my podcast now. You have to. Or wouldn't you? I mean, why wouldn't you? Who would you? I think it's just like a social emotional thing. Yeah. Is it wrong?
Yes, sir. Is the soil in your word bank? Yeah. Yeah, use do the process of elimination, because I think you'll need to use soil. I will tell you that soil does not go there. So do process of elimination, see if you can figure out. No. Yeah, what's up? I think it looks good so far. Thank you, I appreciate you. Been working a lot. Where you getting there, man? Good. Are we up with time? Nice shirt. Oh, you left me a cool pen. The heck is this?